Our next speaker and the last speaker of this conference is James Smith, who's going to speak a little bit about what I think pharmacy and biomedical applications of
Hey, good afternoon, everyone. Thank you for staying for the last. My title is a little bit different than what's on the menu, but it will cover pharmacy and biomedical sciences area. And I thought what I'd do is to give an overview of some of the work we've been doing at Portsmouth over the quite a few years now. So it's been 1993 since we started atomic force microscopy at Portsmouth and STM work. So I thought I'd sort of start with some of that. So my name's James Smith. I am a senior researcher at the University of Portsmouth, and I'm a chemist by training. So I'm not a biologist, I'm not a physicist, so I feel like maybe I shouldn't be here, but let's see how we go. Maybe I will talk about some interesting things what you'd like to pick up on. And following the excellent talk by Sonia, I'm sort of thinking, well, we come on to some biomechanics at the end of the talk, which I think will be interesting. So we've been using AFM mainly in biological systems for many years, and we've been looking at biofilms. As we'll see from the talk, we've done quite a lot of work on hair. Yesterday, Charles Clifford talked a lot about some things about hair, and we started all our SPM studies with looking at HIV-1 reverse transcriptase, so single molecule work with STM with our colleagues in the Harm-Meitner Institute, as it was then in Berlin. And we've done some imaging of secondary structure, DNA, etc. And we've also done work with nano-patterning of surfaces, looking at chemistry and thermosensitive polymers. So I'm going to cover some of these aspects today. STM was our first kind of endeavour in this, and this was really way back in the previous century. We were looking at the HIV-1 reverse transcriptase, which exists as a heterodimer, also a homodimer, and this enzyme attaches to DNA and is part of the reverse transcriptase process. So it has this central hole here, which kind of binds around DNA, and in the literature it's likened to having fingers, palm, thumb analogy to grip to DNA. And so our early imaging was looking at that type of structure, which seemed to map sort of quite nicely onto the crystal structure. And then also we went on to, well, we're using different reverse transcriptase, but this was AMV attaching itself to an RNA DNA hybrid. So we were able to obtain images like that using STM. Then we got our Nano Scope. This was made many years ago. Thermo microscopes, AFM combined STM, and in those days we had I think there was arrangement over at Southampton. They had an STM over here as well with these marble slab on springs to prevent the vibration, and aluminium slats like this to prevent any sort of lateral vibration. And this was built with the help of Southampton University. And more recently, well, I say recently, it's 2003, we got our Nanoscope 4 instrument. Apparently Nanoscope 4 wasn't the one to get, Nanoscope 5 was the one, so we bought it a little bit prematurely. It's got USB ports on it, but they're not, it's USB ready. So it's anyway. And in fact, this work here was looking at thermosensitive polymers, where we were able to do micro contact printing onto mica surfaces. So you kind of pattern it with self-assembled monolayers and able to grow polymers on top of that. And one of the polymers was isopropyl acrylamide, or polynipam, which has a switching ability at a particular temperature, 32 degrees. It switches really from hydrophobic to hydrophilic, which is quite interesting. And we're interested in this in a sort of drug delivery, drug release ability. So we were just looking at the sort of fundamental sciences of putting down a patterned surfaces and switching the temperature. These are just some typical force curves, but you could cycle it between different temperatures. Even with that crude AFM system, you're able to change the temperature and measure hydrophobic or hydrophilic adhesion responses with that and cycle it. That was done with the force volume imaging, or its equivalent, with that particular microscope. And then we went on to force mapping. Okay, well established now, but this was back in 2000, just before that. Looking at polymers, mixed polymers, where you've got again hydrophobic and hydrophilic areas, and able to do adhesion mapping with that type of system. And this was before it was established in the AFM software. So as a whole, this sort of slots into the lectures from Charles Clifford yesterday about measuring spring constants. Obviously, if you want to do anything quantitative, you have to know your spring constant, etc., and there's various equations for that. This particular one was making use of the thickness of the cantilever, and then again Charles mentioned that the fact it's raised to the power of 3 makes it a very error-prone method of determining spring constant. But we have tried other methods. Also, we've gone into a lot of depth of making our own maps of various properties using, we use Visual Basic as a programming because we had total control over that particular system. So we're able to plot various aspects, make our own type of programs up, as we'll see later. You can have a topography image on this side, and then it prints out a corresponding adhesion or whatever property you're measuring, surface energy map, etc. on the right hand side. So we're able to we use Visual Basic to do that type of image creation. Being with the biologists, we've done a lot of work with biocides, looking at the effect of biocide activity on biofilms. So it's just simple imaging, but we've had to kind of develop a system for introducing the reagent into the system. More recently, we revisited some of the very basic images, the imaging modes of AFM. I mean, obviously that you get the topography scan, but even with contact mode imaging, we looked at deflection mode. This is the basic mode you get in the signal from the cantilever directly. And we're able to image this interesting contrast, which maybe we could talk about this at the end, the origin of this kind of contrast on bacteria cells. So this is not the topography image, this is deflection image, the raw signal from the cantilever, which was obscured from normal topography imaging. We spent a lot of time over the years, as I say, looking at AFM of hair, and we've had some of this work was done in collaboration with L'Oreal and Croda, so various companies of interest. So this particular one was SEM corresponding with an AFM image, and there was a particular interest in the kind of surface architecture of hair, which you can see on the cuticle in AFM, but not with SEM. Obviously it's the same region here. And the actual cuticle of hair is quite interesting anyway. You've got this kind of layered structure. So this is, let's say, the outer cuticle, and you've probably got about 4 to 8 cuticles underneath this one, and they're divided into really layers of increasing cysteine content. So this is the hardest layer here, then it becomes progressively softer, and then you've got this kind of cleavage plane here where the hair kind of naturally breaks off to expose a fresh layer of this outer layer here of the cuticle. Is interesting that you last talked, you were talking about the cuticle. I mean, to what extent the hair cuticle resembles a cuticle of a plant. I mean, there must be some sort of analogies.
It's very different composition.
Oh, okay. So, but on hair, that it's known to have this particular fatty acid, 18-MEA, which it's coupled to the sulfur via thioester linkage on here, and it's this particular one, this methyl group, which is sort of 2 carbons in, and it's supposed to give hair this particular surface energy requirement, so it kind of cleaves away. It's like a low energy surface, but it seems to be that they've done fatty acid analysis, but I found this one to be particularly prominent, and not, say, the 19 methyl, or not the straight chain. So we took some sort of interest in that area, to the extent where there's a disease in hair called MSUD, maple syrup urine disease, where there's a lack of a particular amino acid, which then translates to not being able to create 18-MEA on the surface of hair. So we obtained some hair samples from 2 twins, of which one had MSUD and the other twin didn't, and we didn't know at the time. So it's twin sort of DA and DE. It's codes for their names, but it doesn't matter. And they were able to do sort of topography imaging of these. Okay, these are just typical representative hairs. We have many images, and we could see there was a significant roughening of the hair surface of one of the twins, but not the other. And so we're able to predict, because 18-MEA is meant to present this kind of cleavage plane, which twin actually had the disease and which one didn't. So we were able to predict that just based on the structure. So that was interesting. That's some more images of the same thing. I can see a significant roughening in the diseased hairs. These are all diseased hairs compared with the control. Keeping to the hair theme, but we have used other materials. We're looking at friction measurements, sort of quantifying that. Again, at the time of doing this, back in the sort of turn of the century, this wasn't particularly well known for our particular system. So basically it's relying on the lateral force signal from contact mode imaging, and we quantified this using a diffraction grating, of which had 2 different blaze angles. And so you could get a lateral force constant here to relate the frictional force to the normal force applied to the surface. So this proportionality constant. We obtain this by scanning. So in the old AFM system, you had this TFR, which was topography, forward direction, and I can't remember what the R was. Doesn't. Retrace. What was it? Yes, because there was a retrace and an F for forward, wasn't there?
Forward, yeah.
Remember that? Maybe you had that old AFM.
Yeah.
Yeah, or forward. No, that F is for forward, and that R's maybe raw. That's it.
Raw.
It was raw. Then when you process the image, it became TFP. Doesn't matter. So topography in the forward direction and the reverse direction, and the corresponding lateral force in the forward and reverse direction And what we did is we got it scanning and changed the applied load as it stepped down, and so you could control the steps of doing that. And so that was our calibration, and so that with that particular AFM, that was measured in current. I think most AFMs now are volts, aren't they? So it just kind of shows you kind of how old this particular system was. And so frictional force related to, this was using a Montan's law. So frictional force is related to the normal force, and the proportionality constant, depending on how you arrange this, is the adhesion. And so by subtracting the forward, reverse from the forward direction in terms of the pixel positions of the current, you could obtain the frictional force value. And we then went over the hair surface, and we kind of boxed around areas which were identified were different substructures, and we could obtain those momentum plots, and we could, as we might expect, we had the gradient of this is our friction coefficient, and that related to what we would expect. So we had the values we got from it were what we would expect, and we could produce these various types of friction map and the adhesion map. So I won't go into too much detail, but you could obtain basically the friction coefficient map here. Interestingly, the friction coefficients were really quite low, what we would expect, but there is some argument that friction coefficient on that scale is different from the macro friction coefficient. I'll skip that one. Going back to that 18MEA monolayer surface stuff, we tried to construct our own monolayers on surfaces. So we grafted we synthesized actually the fatty acid, and we converted it to the acid chloride, grafted it onto some mica, which was terminated with these SH groups, and did some adhesion measure. That's the synthesis we had to do. It's quite a long, lengthy synthesis. And then we did adhesion plots. These are just, again, typical versions where we always compare distributions of adhesion rather than single ones, but these are just some examples. And we saw that the 18MEA had a particularly lower adhesion than the straight chain analogues, and even this 19MEA, it seemed to have a difference. Again, these are just a few typical ones. These are a bit more representative of what kind of adhesion data we got. So that was some quite interesting work we did there. We've played around with different aspect ratios, because a lot of AFM images are square, or hair lends itself to looking at these various parts. And we're working with some companies looking at before and after type studies, so bleaching, so able to image, have a tress of hair, take a hair sample, a particular hair strand out, image it, put it back in the hair tress, do the cosmetic treatment, get the same hair back out, get the same area, and then image it again afterwards, which is quite some achievement, but we did produce a paper on how to do that. And so we could actually do before and after a treatment. So it's not simply just adding a treatment to the AFM stub, if you like, but actually putting it into a hair tress and treating the whole thing. And looking at sort of friction images as well. Various conditioner products as well. Surprisingly little difference. I know Charles presented a lot of images yesterday of dramatic differences in treatments, but we didn't quite see so many. This particular leave-in conditioner product, you could see on the cuticle quite nicely So that was an obvious difference, but typically we didn't see that sort of thing. And again, keeping the hair theme, although we've done other things, we played around with different ways of presenting AFM data. So rather than just your sort of two-dimensional scale, actually use stereo microscopy. So I don't know if you've done these things before, but if you manage to stare at it and get those two spots to create a central spot, and then kind of look down, maybe the 3D structure might pop out at you. Maybe. It worked on the laptop the other day, but I don't know how
You have to go very
does
far.
it. So maybe. So
You have to go very far.
I don't know if you can see those magic line pictures.
How far about this?
Anyway. So that was a bit of fun. We've also played around with, for sort of marketing purposes, playing around with sort of getting images presented as kind of movies. Again, rendering the sort of three-dimensional data set. So this is really just for kind of show, really, but not particularly any scientific value. But you can get some quite clever software to do this automatically, but we didn't manage to get any kind of. We've identified some software which might be useful for doing it, but we haven't really pursued it. So this was just using the what software was it? Just the one which came with the AFM software, the Brooker software, just rendering the zoom and the XYZ coordinates. So it took a bit of time, but the student was quite happy to do it. So it's gonna, I think there's a few more of these. Got a bit. Buccal cells, these are cheek cells, and just taking examples of that. Just again, it's just presenting the data in a slightly different way. Captures the imagination of different types of people you might want to impress. Not this audience, but done various things with nanotubes. So various types. I think these are silver nanowires, but silver is obviously a good microbial has sort of biocide properties. Okay, one more. The blood-brain barrier, very important in the work we've been doing with neuro-oncologists, how to get drugs into the brain, because there's this natural barrier. So this it's made up of astrocytes and other types of cell. Again, so this was just for a bit of fun, really. We've done some more serious things, protein-protein interactions, derivatizing the AFM tip to have different parts of a molecular motor. So this is a molecular motor which pours DNA through. In fact, this work was done with MPL in the very early stages, so sort of turn of the century, and where they had this particular subunit covalently attached to a tip by these peg linkers. So you've just seen all that protein-protein force pulling work. The other part immobilized to a mica surface using this sort of polyol lysine. And and then using dynamic force spectroscopy, and you can obtain information about the dissociation rates, the lifetime of the bond, etc. So we touched on some of this yesterday. So you're able to sort of quantify some of those aspects using AFM. Again, so this is that particular system. The red curve is the pulling curve, stretching the peg linker, obtaining these curves at different loading rates, so different velocities, and the spring constant for this system. And you're able to obtain these kind of plots of frequency against loading rate with different forces. And from that, you can plot a y equals mx plus c type plot, so loading rate as the x, and then the force, and you're able to obtain these parameters for the energy of the bond, etc. So it's more a kind of, we didn't really do much with that other than just kind of prove that we could obtain those types of measurements with our particular AFM system. And recently we've looked at brain tumour cells, because we across the corridor is the neuro-oncology unit. So this AFM setup is from JPK Instruments, which they lent us, which was very nice of them. And we were able to sort of push into cancer cells and various controls. This had a small micro bead on the end of the tip glued on, so we had a sort of known geometry. We could position it above cancer cells, SMB19s, which are the grade 4 gliomas, and the corresponding astrocytes, and using the classic, maybe we shouldn't be using that system, we can obtain the Young's modulus. And we had lots of conversations yesterday about whether we should be using the word stiffness or Young's modulus, but I use it here, stiffness in quotes. Stiffness is in newtons per meter, and so it should be a modulus, but when you talk about Young's modulus to various cancer research people, it's a slightly different language, so let's keep it on. I did think about changing it last night, but I left it. So we got these types of adhesion data using Young's modulus. We found it to be log normally distributed, like it often is. The paper by Cross et al., who did work in this area. And so we did a log of Young's modulus to get the data normally distributed, so you could do kind of the right stats with it. And we found, so in fact this was done with knocking down CD44, which is a protein which is upregulated in cancer cells, and by knocking down this, and it links to the cytoskeleton, so the idea was, if we knock this down, would it change the mechanism of the cytoskeletal properties, which we obtained immunohistochemistry images alongside. And we could see that on the nucleus of the SMB19 control, this is not knockdown, this had a larger Young's modulus than the knockdown. We also saw this difference with the on the nucleus and on the off the nucleus areas. So on the nucleus was generally had a lower stiffness than off the nucleus. And we've been thinking about why that might be, and one of the parameters is vimentin, one of these intermediate filaments, which it tends to kind of form around the nucleus So that might be a reason why this why it's softer on the knockdown cells compared with on the nucleus here. But it's very much a kind of model in progress. While we're doing these studies, we also looked at the heights of this leading edge of the cancer cells, the melapodia, because when we use this zero force imaging with that JPK Nano Wizard instrument, we found that this periphery was very much larger than the control cells. So by measuring the zero force height images of the SMB cells, we used two particular cell lines here. These are still the grade 4 tumours. These had higher heights than the control. So we had two control astrocytes, which were non-neoplastic. So these had a lower heights here. And this was a grade 2 tumour, which was obviously not the grade 4, which had the poor prognosis, but there's a sort of progression, obviously, going from grade 2 to grade 4. So that seemed to have a kind of lesser height, which was kind of interesting. So again, we're kind of early stages of looking at that. So that's some of the studies we've been doing at Portsmouth, quite varied, and there's lots of others, but obviously I haven't gone into a lot of depth about these things, partly because I collaborate with other people and I wouldn't like to have that expertise on all the things I've been looking at, but it just gives you a bit of the flavour of some of the things we've been doing at Portsmouth over the years. And I just end with some acknowledgements, like some of our funding sources. A lot of it's commercial, which I couldn't put there too many results on that front, but so a lot of the work these days is done with the brain tumour research group at Portsmouth. Thanks very much.
Thank you very much. It was quite interesting. Is there any questions or people asking?
Over the last few days, we've seen some slides on hair, and I mean, this may be a practical question. Do you have to clean it in some way? Because it looks, I mean, I look at surfaces of silicon and it looks just as flat as, just as clean, not flat as hair.
Yes.
Do you clean it in some way, or do the people in Procter & Gamble have like some way to?
It depends what we want to investigate. If it's more the kind of fundamentals of hair, then we tend to have a kind of SDS 1% solution, I think it is, and then clean that ultrasonically for, I think that's 70 minutes, and then wash that with water, and then dry it. So it's quite subtle.
So it's not people that you get that has like very clean hair and you just.
No. Unless
it doesn't naturally come in like that.
You
have to
for some reasons that's what I'm doing. Or sometimes you want to strip off that 18-MEA layer and look at what's underneath, and then there's procedures for doing that. But, various kind of bases.
I think the cuticle being hydrophobic means that when you wash it, that's the trick of the hair. When you wash it, everything comes off just because of the tension of roots. The surface tension of water.
Surface energy. But even then, some of the things you wash it with can actually leave deposits on, which is also of interest. So.
The local structure seems also have to do with that. So like dog hair is very different if you look at the structure. Where people have done that with AFM. L'Oreal has extensive AFM program in looking at hair with AFM for many years. Actually, it's fascinating, and they look at all the structures of hair and dogs, and it's fascinating. You can find this stuff. It's great.
I heard at NPL they were some years ago they did some study on cat hair, but it wasn't on the treatment of hair, but on what they fed the cat.
Probably.
and finding out how
Yeah, yeah, no, it's fascinating.
quality of the hair.
It's fascinating.
Interesting. Yeah.
I wonder if Kelvin will show us something interesting about that hair and why it's sticking out. It's a good question.
Yeah, sorry, I didn't catch with hair. Did you image it in air or water?
We've done both, but
Is
a
there
lot of it's
something
done in
about
air.
water, can it change it, or could you put your shampoo into the imaging water and then observe the...
You can do. We haven't done a lot of that. It's quite fiddly with our particular system, but I'm not sure if you're familiar with that Nano Scope 4 setup. It's the actual wet cell is very quite fiddly to use, etc. But maybe if we had the JPK system where you have this kind of petri dishes of samples, it lends itself. Yeah, it's much more. Yeah, certainly gets swelling. I think how the cuticle swells is of interest. Do the cuticles lift? You get this kind of classic cuticle lifting, but is it lifting or just swelling or combination? Is there a void underneath which opens up penetration? We have done some work where we look at cross sections of the hair and looking at penetrations of dye into hair. So we've done some of that sort of work. I'm sure a lot's been done commercially, but they're not obviously publishing it. But
Couple of questions. So I was thinking with these liquid experiments, are they done at ambient pressure, or are they done different pressures just to see what happens?
with what study in particular, or
For instance, I was thinking about
the cancer
tumor
cell
cells,
stuff?
yeah.
Yeah. This was done in just in physiological, in the growth media to grow the cells. So we had a glass bottom petri dish of the cells, and you can even control the gas flow on that. So you have like 5% CO2 to keep the right environment. I don't know if going back to some of the questions yesterday, where the imaging done within 45 minutes, wasn't that otherwise the cells die, but they're certainly still moving, so maybe that's it probably by the time we kind of finished certainly the experiments were done within a few hours, but because you choose the neuro-oncology labs next door with tissue culture, then bring them in, get on with the imaging straight away. So not controlling pressure as such. Or you mean the pressure, applied load pressure, or atmospheric? Yeah, no control there.
Also related to that, I was thinking that we have environmental AFM and we study different gases. I was thinking if having different gases will affect the stiffness of cells.
In fact, if you want to keep cells happy, you need a CO2 pressure. We do put in our experiments with flow CO2 because they need oxygen and they still need oxygen.
Yeah, so we're trying to mimic what we do with our live cell imaging microscope, which is along the side. So we've got this set up here, and literally in the next bay we've got live cell imaging, which is used pretty constantly. So we get the gases and just bring them across, trying to mimic that same environment.
The other thing is I like a lot the 3D videos about things, and I think it's good that Andres is here because he was developing something.
I 3D printed it, the data, and so you can get the STL model out of it. I can send you the script if you already have it.
Yeah, that'd be great. Yeah.
Yeah, I think that this conference just show 3D image of cell or something would be great.
Yeah, well, it's just sort of exploiting all that because you've got three-dimensional data, but it's never really exploited to its full extent. You just get the square orange
Yeah.
Yeah, so
image.
machine
So,
able to either put color on the 3D.
Yeah.
Any other question?
I've got a question. You said these measurements you did them in cell culture medium.
yes.
And cell culture medium is quite viscous, it's quite thick.
Mm.
So one of the problems we had when we did this was that it was very difficult to assess what was the contact point with the actual cell membrane and what was just a squeezing viscous media against the cell membrane. So if how you determine the contact point is very important to determine the mechanical properties.
Yes.
Of the cell.
Yeah.
So
Yeah.
did you encounter a problem with
We
that?
did. In terms of keeping it brief, I've left out the force curves, but they were, quite fairly shallow. Actually identifying what that. The poster outside of it. Is it still up?
No.
No. Okay. Phew. In fact, I don't know if you saw that poster yesterday, but there was, in fact, it's the same GPK software of putting the fit onto the. We got the equation.
Yeah, because
Yeah,
you're
using this
you
type
use,
of equation fit.
you use hertz.
Yeah,
Normal hertz, which is fine if you know where you're doing it and if it's not very big. The problem
Yes.
is that if you're convoluting with the interface, which is usually a power law that does not follow that, you have very bad fits.
Yes, yeah,
So there's several ways
Yeah.
around this. You can look for the goodness of fit, but
yes,
then you assume your model is correct.
yes, yes.
Then there are several possibilities, and it's not an easy one.
Yeah, I certainly will look at this in more depth based on.
It's not an easy.
No. Lifetime of work.
No.
No.
You just have to do the right fitting.
Yeah.
Is there any more questions? Now let's thank the speaker again. And this was the last of this conference.